Okay, so you should have the notes out in front of you, and I feel pretty confident that we got to this place yesterday. This is where I feel like we left off. Okay. Now, because this is where we left off, I want to talk to you about something that needs to be addressed. Okay. All right. So first things first. We left off with cations and anions. Now, a cation is a positively charged particle, and an anion is a negatively charged particle. But I think an easy way to remember this is if you actually know why the charges matter. So, if you have a neutral atom, it means that the positive and negative charges are equal. So, in order to have a neutral atom, you have the same protons and the same neutrons. Okay? And by neutrons, I mean electrons. So, protons are positively charged, electrons are negatively charged. And if you remember, for the last couple weeks, I've been saying the atomic number is the number of protons, that never changes, and it's the number of electrons, at least where we start with electrons. So in order for an atom to be electrically neutral, we have to have the same number of protons and electrons, okay? And if you look at your periodic table, get that periodic table out. The one that you should probably be looking at is this one. Now, you get that out and you look for the protons. So I've got two examples here. I've got 20 protons, which tells me what element is it? It's calcium. So I'm just going to write calcium down here because I know that calcium has 20 protons, and everything on the periodic table starts out as electrically neutral. It has the same number of protons and electrons. But the crazy thing is that most of the elements on the periodic table aren't in their elemental state in nature. They are in compounds. Now, look up if it has 16 protons, what element am I dealing with? I'm dealing with sulfur. So I'm just going to put that down here. So now we've got calcium and we've got sulfur. And I circled the valence electrons here. So calcium has 2 valence electrons and sulfur has 6 valence electrons. Now, yesterday we talked about the magic number that all of the elements want to have in order to be stable. What's that magic number? It's 8. They all want to have 8 electrons in their outer shell, and they're either going to give up or take on or share in order to make that happen. Now, when they give up or take on, that's when they are changing the neutralness of the atom. So if you take a look at calcium and its Bohr model, do you see how there are 2 electrons in its outer shell, like 2 valence electrons? And then there are 6 in sulfur. It doesn't take a mathematical genius in order to figure out that 2 plus 6 equals 8. So here's what happens. Calcium gives up these 2 electrons, and sulfur takes them on. So now, if you pay attention, I have 8 electrons in the outer shell, which means it's stable, and 8 electrons in this outer shell. Well, that's great because now they're both stable and they've created a compound. The problem is that they just gave up electrons, which affects the overall charge of the atom. So now calcium started with an electrically neutral atom, 20 protons, 20 electrons. It just gave up 2, which means how many protons does it have? It didn't give up any protons. So how many protons does it have? 20. It has 20 protons. How many electrons does it have? Because it just gave them up. It has 18 electrons. Well, now that makes all the sense in the world as to why you just created a cation. Because what particles do you have more of? Protons. What's the charge of a proton? Positive. A cation is a positively charged particle because you give up electrons. And when you give up electrons, now the overall charge of the atom is positive. Well, now let's go look at sulfur. Because sulfur just took on 2 more electrons. It started with 16 protons and 16 electrons, right? But now it has 16 protons and how many electrons? 2 plus 8 is 10. 8 plus 8 is? Well, I'm sorry. 2 plus 8 is 10. 8 plus 10 is 18. So how many electrons now does sulfur have? 18, which is 2 more than it was born with, if you will. So what is the overall charge of sulfur because it took on more electrons? It's negative. That is how you create cations and anions. And on your periodic table that you're looking at, do you see how this entire family is +1? That entire family will give up 1 electron. Do you see how this entire family is +2? What are they going to do? Give up 2 electrons. Now, when they give up their electrons, now all of a sudden they don't have an electrically neutral atom. Now they have extra protons. Okay. Now, does it make sense that if it is a +1, remember what's the magic number? 8. If it is a +1, these guys are going to probably form bonds with the -1s, right? +1 and -1. They have 1, they need 1, let's form a bond. These +2s, what are they going to probably form bonds with? The -2s. These +3s, what are they probably going to form bonds with? The -3s. Now, that's great. Except the fact of the matter is that we have way more compounds than we do the +1s and the -1s. For example, C6, H12, O8. In this organic compound, in order to make sure that it's stable, we have to add enough carbons and enough oxygens in order to balance out the entire compound. So sometimes, like when we combined lithium and fluorine, we will have a 1-to-1 ratio. Lithium is going to give up 1, fluorine is going to accept 1. But sometimes we will have a 6-to-12-to-8 ratio, depending on how the bond occurs. And that is what we're going to continue on today. So let's take a look at your notes, because your notes, I pretty much just explained all the things that you need to have in your notes. But let's go through and finish. So I just explained cations and anions. Now, lithium has 1 valence electron, which means, is it going to give up 1 or take on 7? It's going to give up 1. If it gives up, is it creating a positively charged atom or a negatively charged atom? It's creating a positively charged atom because as soon as it gives up its electron, now it has more protons. Okay, what about nitrogen? Give up 5 or take on 3? It's going to be easier for it to take on 3. It might seem like more work, but it's actually less energy because it wants the electrons. Remember how we talked about how the atoms on the right-hand side of the periodic table want the electrons more? Well, it wants the electrons. So really, it wants the electrons because that balances out its energy. Okay. Now I gave you that periodic table, so I think this is where your notes might pick up. I gave you that periodic table that shows you that elements in the same group have the same number of valence electrons, which means they're all going to form ions the same way. So because they have one valence electron, they're going to give up one electron, which means they'll form a +1 ion charge. So lithium's going to give up an electron, it's going to be +1. Sodium's going to give up an electron, it's going to be +1. Potassium's going to give up an electron, it's going to be +1. So you have this. Now you'll never have to use a test in this class without this periodic table. You'll always have this in front of you, okay? I don't expect you to memorize it. This right here is the valence electrons. These are the ones that are in the outer shell. This number here, the +1, the +2, that is the oxidation number. And that tells me if I give up 2 electrons, then I'm going to be positively charged with 2. That's going to be my overall charge because I just gave up electrons. I gave up all the electrons that I was born with. And now I have more protons than I do electrons. So these two numbers are related to each other. If you have 3 valence electrons, you also are going to be a cation. If you have 5 valence electrons, in order to get to 8, you're going to take on in order to get to 8, in order to be stable. So these two numbers are just a different way of saying the same thing. I need 3 electrons, so I'm going to take 3 electrons. Okay. So oxidation numbers, the charge of an ion within a compound. And then as you look at your periodic table, you'll see group 1 has a +1 charge and group 2 has a +2 charge. We'll skip the transition metals because the transition metals all have variable oxidation numbers. Group 13 is +3, 14 is ±4. Remember, halfway to 8 is 4. So group 14 will either give up or take on. They don't care. They just want to be stable. Group 15 is -3, group 16 is -2, and group 17 is -1. Okay, now we're going to spend a little bit of time on electron dot diagrams. You've done these before, right? The Bohr models are the big ones that we just got done doing. The dot models are just the valence electrons. That's all we really care about in bonding anyway. So it makes things kind of easy. Here are what the Lewis models look like. Remember that you use the inside with the atomic symbol. So now we don't draw the nucleus and place the protons and neutrons. Now we just put the symbol in. And then we determine the number of valence electrons by looking at the group number. And the valence electrons is the amount of dots. You will never have more than 8 dots in a valence electron because the maximum number is 8. All you have to draw out is 8 dots. And then the way that I kind of told you guys to do this is to fill it by 12 o'clock, 3 o'clock, 6 o'clock, 9 o'clock. Fill one time around, then come back and fill 12 o'clock, 3 o'clock, 6 o'clock, 9 o'clock. So my example is going to be nitrogen. So the first thing you have to do is know nitrogen symbol. What is nitrogen symbol? And now, right above nitrogen, you're going to look for its valence electrons. How many valence electrons does nitrogen have? And again, if you're not sure where I'm getting this, look at your periodic table. Nitrogen, how many valence electrons does it have? 5. So how many dots is nitrogen going to get? 5. Okay, I'm going to give you about a minute to practice these 4. Okay, so here's what you should have. Well, maybe. Here are your symbols, so you should have 1 dot, 4 dots, 7 dots, 5 dots. Now we get to the fun part. So that's how you do a single element. You also get to do electron dot diagrams to show bond formations. So the first thing you're going to do is draw the electron dot structures for the elements. Then you're going to transfer the electrons using an arrow from the metal to the nonmetal. So when we deal with ionic bonds, it's always a metal-nonmetal combination. Metals are always going to give, nonmetals are always going to take. You're going to add the elements as needed, and I'll show you that here shortly. And you're going to continue transferring until all atoms are stable. Then you want to write the chemical formula using subscripts to show how many of each element were needed. Okay. So now I think you have this as an example. So the first thing I want you to do is to write the symbol. What's the symbol for sodium? Na. Now, how many dots, how many valence electrons does sodium have? 1. Symbol for chlorine is Cl. How many valence electrons does it have? 7. Now again, I ask you, what is the magic number? 8. Not rocket science here to know that sodium is going to give its electron to chlorine. That's all you're going to do. Draw an arrow. So this is using the Lewis models in order to show bonding. Now the last thing that you have to do is to write the chemical formula. In this case, there's 1 sodium to 1 chlorine, so the formula is NaCl. Okay. What compound will form between aluminum and chlorine? So symbol for aluminum is Al. Aluminum has how many valence electrons? 3. Chlorine, Cl, 7. Now, I also don't think this is rocket science, but do you see how aluminum is going to give one of its valence electrons, and then chlorine is full, right? But then aluminum's in a little bit of trouble because now it has 2, which is a problem because what it wants to do is give up 3. So now we don't have an even ratio. It's not going to take 1 aluminum in order to balance out one chlorine. So what do I have to do? Add another chlorine. And then, look, aluminum is now going to give one of those electrons to chlorine. But wait, there's more. Because aluminum wants to give away 3. Chlorine only has room for 1, which means what do I have to do now? Add another chlorine. And now, when we go to write the chemical formula, now it's not a 1-to-1. Now it is a 1, 2, 3, which means the chemical formula is AlCl3. In order to make both of these guys stable, I need 3 chlorines. Because you can't just give one up and leave it like that. That doesn't work. Okay. Now, I would like to work through number 1 and 2. So, for the first one, what am I dealing with? Help me out here. I forgot. Potassium, which is K, and chlorine, which is Cl. Potassium has how many valence electrons? 1. Chlorine has how many valence electrons? 7. Now, what's going to happen here? Whoops, give me another one. Potassium is going to give to chlorine, which makes the chemical formula 1-to-1, so it's going to be KCl. What about the second one? Magnesium and fluorine. Symbol is MgF. Magnesium has how many valence electrons? 2. Fluorine has how many valence electrons? 7. So I can give one of magnesium's over here, but what's my problem? I have an extra, which means what do I have to do? Add an extra what? Fluorine. So I add an extra fluorine with its 7 around it. Now what happens? I can give there. What's my chemical formula? What's my ratio? 1 Mg, how many Fs? 2. How about you do number 3? So for aluminum and nitrogen, how many does aluminum want to give up? 3. How many does nitrogen want to take on? 3. So that is also going to be an ALN. So like a 1-to-1. But now I've got magnesium and phosphorus. This is a goodie. So magnesium has how many valence electrons? So I got magnesium, and it's got 2 valence electrons. And phosphorus has how many valence electrons? 5. 1, 2, 3, 4, 5. Okay, so I can give one of these here. I can give one of these here. But now I've got a problem because magnesium has an extra one, right? So what do I have to do? Add another magnesium, which is going to have 3. So I can add that one here, but now I have a problem because magnesium has empty ones here. which means what do I have to do? Add a phosphorus. Well, that's cool. I can add these guys, but now I have another problem. So what do I have to do? Add another magnesium, which is going to give me what? 2, right? 1, 2, 3, 4, 5. What did I do? Something wrong. You don't need to make another phosphorus. So what did I do wrong? Oh, yeah, that's what I did. I put 3 instead of 2. Dang it, Tammy. Okay, so now this should be fine because I should have one there. Yep. So now my ratio, Mg what? 3, P what? 2. Sorry about that, people online. Okay, that's where we're going to end today.